on. So we've got 2 more demos, and they're going to follow a very similar format where we're going to walk through the CR3BP frame, and that's going to be the simplified model, and then we're going to finally do an ephemeris model that shares that same basis vectors, and it will again be you've done the hard work up front on the simplified CR3BP model, so up-resing things to a higher order fidelity is almost trivial. So I know we even worked on deriving this, well, I guess implementing this yesterday, so we won't spend too much time. I suspect everyone here is at least familiar with the CR3BP. We addressed it in day 1. It's got your planets, P1 and P2, or your planetary bodies, I should say, constrained in a rotating frame. The origin of your frame is at the barycenter of those 2 bodies, so the Earth-Moon or the Sun-Earth. And you're deriving these things in a rotating frame. So you did write your own implementation of this yesterday, but it does also come in the asset Astro library. It's a simplified model. So the CR3BP is an autonomous system, so we don't have to have a frame because there's no ephemerides in CR3BP. So let's do one more script, and we're going to change our imports. This should probably seem familiar at this point. We're coming from the Astro models. We're going to import CR3BP. We're also going to do a low thrust spacecraft within the CR3BP. So we want the CR3BP model, which just has the states of CR3BP, and CR3BP underscore LT is a low thrust implementation of the circular restricted 3 body. So now you all know from day 1, that means we've got the same states that we're getting the same ballistic dynamics, but now we also have an acceleration that's tied to the U vector. How we handle that U vector is handled slightly different here, though. We're going to use a thruster model from the Astro library. So the next import that you need is from the astro.extensions.thruster models library, and we're going to import low thrust acceleration. And then one final thing, just of our utility functions that we're doing here. We've already imported matplotlib. In this use case and in the next scenario, it's going to be a lot easier to visualize things with a 3D plot that you can click and drag things around. So we're going to import the 3D functionality from matplotlib. So MPL toolkits imported as mplot 3D. So now we can just go straight into configuring the model and defining our constants. So again, simplified, we don't need the frame. So this model, we now pass in, so you've got P1 and P2, the 3rd planetary, or the 3rd body in the problem is our spacecraft. So to instantiate the CR3BP from Astro, we pass in the dimensional gravitational parameter of P1. So in this case, we're using our constants library to do mu of Earth. The next one, we're going to use the mu of the moon. So P1 is the Earth, P2 is the moon. And then we're going to pick a characteristic length. So gravity 1, gravity 2, characteristic length. It makes perfect sense to non-dimensionalize it by lunar distance. So now distance between sun and moon is unity. And that distance dimensionalized is lunar distance. Did I say sun, Earth? Sun, moon. Wow. Happy Friday. It's the Earth moon system. So anything that I said that had the sun, I meant the Earth moon system, and I apologize. So once we've instantiated the ODE, we can again get an integrator. Again, this is the ballistic problem. Get an integrator, so CR3BP and tag. And then let's get all of these dimensional structures again so that we can not work in dimensional units, but get it appropriately non-dimensionalized to the CR3BP frame. Okay, that's hopefully very trivial at this point in time, so we'll move on. So what we're going to do now is we're also going to create a low thrust engine and instantiate a low thrust engine model. And we're going to use that to instantiate the CR3BP with a low thrust engine spacecraft. So that lives within that thruster models section of the library. This low thrust Excel thruster model can be instantiated using non-dimensional acceleration or dimensional acceleration. It's entirely user's choice. So you just need to set a Boolean flag to false for the one that you're not using. So how it's written now, it expects either, if you're doing a non-dimensional acceleration to input, it expects the non-dimensional value, comma, false, so it knows you're not using dimensional, or vice versa. What we'll do here is say, we're going to give it a dimensional input, so we're going to do low thrust accel engine, false, so it knows this is not a non-dimensional term. We're giving it to you in dimensions. This model is responsible for non-dimensionalizing it, and then hand it the dimensional accel. So this is 0.005 meters per second acceleration, which is fairly sporty. It's just what I've used for this example. You're going to want to model if you're modeling actual hardware, you'll know what your engine's acceleration can produce. And of course, there's more, you can write higher fidelity engine models, and we're hoping to add those in soon to the Astro model to have things like the change of acceleration with mass decrement.
So since you semantics me a lot, I'm going to semantics you. CR3BP low thrust is inherited from CR3BP.
It uses the same.
What you're trying to say is the instance that you're instantiating is going to be entirely independent of the other instance that you're instantiating.
Absolutely.
You're making two different separate objects that are independent. They're going to become something else, do two totally different things.
Yep.
If you go look under the hood in the Astro library, CR3BP low thrust does inherit from CR3BP, so they are not independent technically. The classes themselves.
The class descriptions. Yes, we're instantiating. So yeah, once we've instantiated CR3BP low thrust, now you've got the three control vectors like we had in those exercises yesterday. Right. But yes. Right. Yeah. So yeah, we've now instantiated a low thrust engine model, and the CR3BP low thrust is an instantiation of the CR3BP problem with that engine. So yes, the CR3BP and CR3BP LT that we've got instantiated are handled as two different objects that have been instantiated. So we're going to want a prograde control law for just getting some control values as an initial guess. You'll see later in this example, we don't fly even remotely close to a prograde, but this is a way to at least just populate the control values for an initial guess generation. It's a very simple vector function argument that I think we even wrote yesterday in one example. So you're expecting three vector function arguments. They're going to be your position or your velocity, and you take the unit vector of that. So when we create the integrator for the low thrust problem, we're going to instantiate the CR3BP low thrust integrator with that same time step as what we had in ballistics, but now we're going to have the new control law for prograde and pass it, excuse me, pass it the X velocity, Y velocity, and Z. So we've got our control law. Let's generate an initial guess now. So we're going to take initial conditions. Again, this is in the demo script. This is demo 3 on day 2, so that you can just pull the initial conditions if you'd like. Actually, I didn't even finish so that the rest of this was legible. All of the initial condition for the halo orbit is not in this screen. Grab it from that script. So what we're going to do is set up the initial condition and find a final time for a lunar halo orbit. This is an L1 northern halo. Once we've pulled those initial conditions, we're going to integrate them for the period that we were given. Again, notice integrators go to absolute time. So we're doing a relative time by taking the initial conditions time and adding the period to it. So we're going to integrate that and turn that into a NumPy array. And then we want a lunar initial condition. This problem is going to be, we start in a low lunar orbit, and we're going to then use the low thrust engine to raise from that low lunar orbit and do a low thrust engine transfer out to a halo orbit to rendezvous with the halo. So the halo orbit and the low lunar orbit are both going to be ballistic orbits in the CR3BP, and then obviously the transfer is going to use the CR3BP low thrust term. So what we're doing here is pulling the initial conditions for the starting orbit and for the final halo orbit that we're targeting, establishing those conditions, and then integrating them. So now we have time history of where we are starting from and where we are trying to target. We'll give just a few minutes. This is a pretty quick thing to pull over. You're already pulling in the initial conditions, so you're right by the solution key here. Here's an example that I'll flag. Also, there are, when you've created the CR3BP model and instantiated it from Astro, it has the property. It's a class instantiation, so it has properties such as capital P, P1, and P2. So what's the position of the primary planets within the frame, and it has L1, L2 through L5 of where are the like Lagrange points positions within that. So here our lunar orbit is even just taking P2's X location, adding some distance from it in the X component, and then doing an arbitrary velocity in the Y direction of the frame. So here's a use case for pulling the position data that is stored as a property of the model.
You separate a lunar halo, but property of both.
Precisely. So yeah, we'll move on here. So if you the next thing we're going to do is generate an initial guess of the low thrust spacecraft that's going to transfer out, and then we can just create a plot and plot all of them to show it. So for the burn phase, or what I'm calling the burn initial condition, that's the low thrust engine that's burning continually. So for that initial condition, we can copy the end of the low lunar orbit initial guess. But recall, as I've probably beaten to death at this point in the training, you need to know the dimensionality of the functions that you're calling. So the ballistic problem is dimension size 7 because it's your 6 states in time. The low thrust problem has 3 more elements to it because it's got a control vector. So even your initial guess, initial condition that you integrate as an initial guess needs to be of that proper size 10. So to get an initial condition for the low thrust model from the end state of a ballistic model, I use NumPy concatenate. You can use NumPy stack, call whatever way you would like to concatenate these variables so that you can take the end of the lunar ballistic state. So that's now got your position, velocity, time, and then append to the end of that 3 control variables. Remember, we're going to integrate those in an integrator that has a control law appended, so we can put any values we want as the initial condition controls. The U vector is going to get overwritten every time step in our integration to follow that prograde control law. So I just 1, 0, 0 here. You could do all zeros. You just need the proper dimensional size of your initial condition. And then we do exactly that. We run it through, we get the burn initial guess by running it through our low thrust integrator, and we just run it out for 24 hours. And when you plot it using the plot at the left, notice the plotting syntax has changed because we're doing a 3D plot just so that you can kind of click and drag and zoom around these 3D orbits. But you can see we've got this blue halo orbit that's out of plane. It's an L1 orbit. We've got the low lunar orbit close to a planar lunar orbit in green, and then we've got our initial guess in red. Alrighty, so I'm assuming that everybody was able to get that. This is all just initial guess formulation. So one other thing we're going to do here to set up for our problem is we're going to actually set the halo orbit as a interp table. So this is, I know we went over interp table 1D yesterday. where you can do just a single data input and then point out the axis of where your lookup parameter. Another syntax you can use is have a vector of time states and then a vector of the interpolated states you're trying to pull. So in this case, I break apart because we turned Halo IG into a NumPy array. We can use NumPy slicing and just get the states of the halo orbit and the times of those states by slicing it this way. So then we have a halo orbit table. So we've tabulated and have a spline fit of the time history of this orbit we're trying to get to. Notice I did kind equals cubic, so that means we're twice differentiable spline fit for this. And then I pull this rendezvous point. So we are going to formulate this halo transfer as a rendezvous problem with that target orbit that we propagated. However, we don't necessarily need that orbit to be in a specific position at a specific time. We're in the CR3BP, it's entirely an autonomous system, right? So you can have time of 0 or time of 1 billion, and that state is going to lead to the same downstream state with propagation. So how we're going to handle that in this is we're actually going to make a rendezvous table constraint similar to the rendezvous we've gone over previously, using the halo table as what we're targeting. But instead of passing in our dynamic time of where our phase is at, we're actually going to have a static parameter in our phase. And we're just going to bound the static parameter to be within scope of when the halo orbit is just defined. And now we'll let the optimizer change the static parameter of where are we looking up the halo table to rendezvous. So essentially the static param of our phase now becomes what rendezvous location on the halo orbit is optimal for our problem. So that's what this rendezvous point is I'm going to say, let's assume we want to rendezvous about 3/4 of the way through the orbit propagation that we propagated out. So 3/4 times your halo orbit total period, the halo DT, means that's now an initial guess. That rendezvous point is an initial guess that we can feed as the initial static parameter point. But asset, unless we constrain it not to, asset will use these static parameters and dynamically change these static parameters in a phase to achieve optimality, which we'll see soon. So as a test, or the last line is entirely just to show syntax or to show how you can use these. We now have a table lookup of the halo orbit, and it's indexed by some time. So it's from time 0 to the non-dimensional period. We can just throw a time into that table, like this rendezvous point that's 3/4 in, and it's going to return the halo orbit states at that time. So if you've been following along with this training, that probably smells like a really good equality constraint for an orbit transfer. So we're going to write that rendezvous constraint now, and this is very similar to what we've seen previously. So it's going to expect 7 arguments, and notice we're going to pass it. We're going to assume that these arguments that come in, the first 6 are going to be states. The last one is the target rendezvous point on the halo orbit. So when we instantiate this as a phase, we're obviously going to pull 0 through 6 of our states for this, but the rendezvous time that we pass in is going to be a static parameter.
So that so that rend time equals arg6 is actually, like arg6 is the time.
Yes, arg6 is going to be the static parameter, which we're going to represent the table lookup time of the halo orbit. And then, of course, once we've computed this target states, is we're going to take the static parameter that we're passing in, find the position and velocity of the halo orbit from the table at that target rendezvous time. That's now our target states, and we can return the difference between. So we're returning a size 6 vector function that seems like a great candidate to apply to an equality constraint to force rendezvous. So once you've got that constraint written, we can move on and set up phases. So go ahead and my plan here is I'm going to give kind of a walkthrough of this. I would like to, and before we ever move on from here, see if you feel comfortable constructing the problem. Now that we know the transfer is optimizing that low thrust phase, so we're going to start on the low lunar orbit, start doing a low thrust phase at some point on that low lunar orbit, and then go out and rendezvous with the halo orbit. So I'll leave time, a little bit of extra time, so you feel free to reference this slide if you want, or if you'd like a little bit more of a challenge, you let this slide serve as kind of an answer key and try and dive in now and write the phases yourself, making sure that you're applying the proper constraints. So it's a 3-phase problem. So once you've written these, you're also going to need to form an optimal control problem to patch them together. So go ahead, and we're going to give a few minutes now to try and see if you can optimize that transfer from low lunar orbit to halo. So this is interactive. Definitely speak up if you're feeling lost or have questions again. Okay, well, Will has it converged in person, so Will gets bonus points for this, but he raised a very good question on transcription mode. So I set LGL5 in the low thrust phase here and LGL3 for the ballistic. There's not any necessarily hard and fast rule for which transcription mode you want to run. We've found within ASRL that LGL5 is kind of the sweet spot. So as you add more polynomial orders to your transcription, it obviously gets more accurate because you're having a higher order polynomial fit between your knot points. But it's also going to run slower because you're increasing the order of what you're transcribing. So LGL3 is going to be the fastest transcription you can use. So if you have not too fast of dynamics, LGL3 is very quick and still valid. LGL5 is kind of that sweet spot of it can handle more stiff ODEs that you're integrating through, or more stiff problems, while not running quite as slow as LGL7 does. So that was, again, an arbitrary choice here, but let's walk through the solution of this. And then I know it's 4 o'clock Central. We are just about done with the training. So let's walk through this and look at the next example then. We're going to close then. So we have the low lunar orbit phase that we're instantiating from the CR3BP instance of the model. We set our initial guess, and we add the boundary value that the front, so the initial condition must be the same as the initial condition of the orbit we propagated. And then we just set upper and lower delta time bounds. So we want it to propagate at least, I chose the arbitrary 30 hours to a maximum of 70 hours as a range so that you can go through the orbit. Then we're going to have the low thrust transfer phase. So we're instantiating a phase not from CR3BP object, but from CR3BP low thrust. Again, I used LGL5 on this. You would get convergence with 357 or central shooting in this. I had a lower delta time bound of around 5 hours, and then set the objective function to be a delta time objective. So that is built in as a method for phase. If you know you're just trying to minimize the time of the phase, you don't need to write a vector function for it. You can just say delta time objective with a weight of 1. Then we set a run. Oh, question? Okay. So then we set the final phase, a rendezvous, or sorry, within this phase, we set a rendezvous constraint using static parameters. So we add a static parameter, and we're initializing it as this rendezvous point, which we said is 3/4 of the way through the halo orbit. And then we do a lower upper variable bound using the static parameter phase region flag. So remember, asset's going to change the static parameters that you've appended to achieve optimality within the constraints that you've applied. So we use the static param flag to say index 0 of my static param, so this rendezvous time static parameter, is going to be bounded to a lower bound of 0 and an upper bound of the halo orbit period. So the static parameter is now allowed to change only within the scope of where the halo orbit has been defined in the lookup table.
That's static. You say index 0, it only has one index, right?
Correct, yeah. In this case, it only has 1. But since you can add any arbitrary amount of static parameters, this is your way to call out we're bounding the static param of some index. So yeah, good point. This input is what index of your static params for if you have, even if you have 1, you just call index 0, but you could have, 20 static parameters if you needed. So we've now got a static parameter to represent when we're rendezvousing with the halo orbit, when on the table we're rendezvousing. So now we just add the equality constraint to the back of this low thrust phase to have it rendezvous with the halo orbit table. Of course, that call needed size 7, right? So we pass in position and velocity states. We don't have any ODE parameters, so that's an empty. And then we're going to pass in the first static parameter. So when we look at that constraint function, the args 7 that's coming in, we do head 6. That head 6 of those args of this rendezvous con are our states. And then we do, I think, tail 1, or however we slice it within that function. That tail 1 is going to be the ODE parameter that we use as time for the table lookup. So then we finally add just some optional controller settings. So you can set control mode. How are you defining the controller? So we set it to highest order spline. You can also do block constant or first order spline. Those are discussed in detail in the documentation for maybe use cases of different ways to transcribe your controls. And then we do a LU norm bound on the controller. So again, this low thrust engine, we don't want going to 0 or less than 0, and we don't want it to exceed 1. So wanted to, question? Yeah. So I wanted us to start on that low lunar orbit, but we don't necessarily know where on that orbit is going to be the optimal time to start doing the low thrust burn.
Right. So how's it communicate?
Right now it's not, because these are separate phases, but we're going to then add these 2 separate phases to an OCP and solve them with forward link equal in the next slides.
But how is LT, like, how do we know the LT phase needs to start from LLO phase?
So on this slide, what we have here, there's nothing constraining it to do that. But as soon as you, when you're formulating a problem, as soon as you have a thought of, okay, how does this phase know that it needs to do something with this other phase? That is a strong indicator. That's not handled on the phase level. That's going to be a link constraint for your OCP. So that our next slide will address exactly that. So we've created the phases, and we've applied all of the phase specific constraints and objectives. But then we'll form an OCP in the next slide and do any phase relative constraints, including we want continuity from one to the other. Okay. So yeah, if we had a fixed position and you said go from this initial state that is just a point on that low lunar orbit, you could absolutely solve this just with this low thrust phase. We wanted to make this a slightly more interesting problem where you're stuck starting on that low lunar orbit, but you can change and optimize how long do you propagate ballistically on that orbit before you turn your low thrust engine on and start the transfer.
What we were talking.
Yes. Yep, absolutely. This is an example of that.
I thought these were all the constraints for down.
Nope. We're pointing out the constraints of the phases, then we'll form them together into an OCP. So one thing I just wanted to point out, I mean, at this point, you've probably noticed it, we're instantiating these phases from 2 different ODEs. And we're going to throw those 2 different ODEs into one optimal control problem. So you can have mixed ODEs, you can have mixed transcription. So in this example, our OCP that we form, next slide, is going to have 2 different phases that are instantiated from 2 different solution space models with 2 different transcription methods, but there's absolutely no constraint on users that would prevent you from doing this mixed modeling approach. You can have it all with this. So yeah, pointing out we've got different transcription modes here. I kind of went over already what this slide highlights of showing we're going to instantiate that static param and give it an initial guess. Think of the value you put into the static param as an initial guess for that static parameter value, but Assets Optimizer will change that static param within whatever bounds you set on it to optimize the problem. So if you don't set bounds, don't treat a static parameter as if it's a fixed value permanently. Asset will change that unless you give it a boundary value and say it must be this value. So since this static parameter is allowed to change, that's the additional term we pass into rendezvous constraint. And notice again a call out of we're doing a low thrust burn, so we're going to do an LU norm bound on the control vector. So the challenge here is what we just gave time for, of construct a transfer from those. There's discontinuity, so you were just asking about that. During impulsive maneuvers, there's discontinuity in velocity. Here, we are saying we're starting at some phase, then turning on a low thrust angle. So that's not true anymore. We can have full state continuity for a low thrust engine or a solar sail or a finite burn engine because you are no longer implying a change in velocity. We're going to have an acceleration added to our optimal control problem that is literally causing the change in velocity over time. And then again, we hinted at link objectives and link constraints here. So here's that final solution. And if we now formulate an optimal control problem, we add the LLO phase and the low thrust phase. And then here we add a forward link equalcon from those phases of position, velocity, and time. So now how we've got our problem transcribed, if the optimal solution is to deploy our low thrust vehicle a little bit further around in that low lunar orbit, there's a constraint on those links that the start of the next phase must be the end of one. So naturally, the way to optimize it is to increase the time that you're propagating the low lunar orbit out. So here we have forced continuity. Now that continuity is enforced, we can solve optimize, and we get this transfer. I'm glad the code you've been given the code and or written this out yourself. I know it looks strange in this projection, so it's a good thing to be able to kind of pan around in 3D to look at this transfer where we go out and then rendezvous with the halo. So then we just print out or return the trajectories. And if you have if you ask yourself, well, where is the rendezvous point? What time are we rendezvousing with? Obviously, it will be the last time of the final state in your low thrust trajectory. But if you had a bunch of other static parameters, or you want this syntax, you can also take your phase and return static params. And obviously our rendezvous state or rendezvous time is the 0 index because there's only one static param. So any questions on this before we move on to the final example, which is a pretty quick example? So again, there's code here of plotting it to generate that plot. This is in the solutions that you were delivered, and saving it off again in whatever format you want. Again, you can do a feather file, a NumPy file, however you want to save your solution.